Hi everyone. Okay, today we're gonna do we'll go through the solution for the hydroxy compounds MCQ quiz. Okay, let's look at question one. All right, let's look at question one. Which of the following alcohols cannot be transformed by this hydroboration process? Okay, so if you look at this compound here, all right, let's look at this compound here. Let me draw it out first. Okay, this is what it looks like. All right, and this is the final product. They put CH3. Let me just draw this side. All right, CHH. Okay, if you did realize, right, they put the H over here and put the OH over here. So it's actually against Markovnikov's rule, because Markovnikov's rule states that the hydrogen will go to the carbon with more H. So typically, the hydrogen should go to this carbon, right? Then the OH should go to the other carbon, because this carbon has two H's, right? This carbon only has one. So this is more like a bit like an anti-Markovnikov's, right? Because you need to know the mechanism. So this is what happens. So just the opposite of Markovnikov's rule. Which of the following alcohols cannot be formed by this hydroboration process? So maybe I'm just going to do two options, A and B, and then for you to take a look. All right. So you start from but1-ene. So but1-ene looks like this. Okay, but1-ene. So this is the but1-ene. All right. Okay, and eventually you get butane-2-ol. All right, butane-2-ol, which is CH3, CH2. Let me just put here. Butane-2-ol means the OH here, and actually the H over here. All right. So you put the H here and the OH over here. So looking at this structure, actually this is like following Markovnikov's rule. All right, following Markovnikov's rule, but this mechanism is like anti-Markovnikov's rule, so it's just opposite, which means A is wrong. Okay, A is wrong because it's incorrect. You cannot form it this way because actually follow Markovnikov's rule. Okay, let's look at B, whether it's feasible. Okay, let's look at option B. We start from 2-methylpropene. So 2-methylpropene looks like this. Propene, right? 2-methyl means the CH3 on the second carbon. All right. So what you get 2-methylpropan-1-ol, 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 which means 1-ol means the OH goes here and the H goes here. So actually, if we look at this one, typically according to Markovnikov's rule, H should go here and OH should go here. But since this mechanism is like anti-Markovnikov's rule, so the OH actually will go here and the H will go here. All right, so that's what you got, which means this one B is actually this 2-methylpropan-1-ol can be formed from 2-methylpropene, yeah, via this hydroboration process. Okay, so that's why the answer is A. All right. Okay, let's look at the next part. Okay, let's look at the next question. Which of the following observation is correct? Okay, which of the following observation is correct? So a reaction with hot alkaline equals iodine to give a yellow solid. Is this correct? This is wrong because you don't even have any of this structure. Okay, you need to have the methyl ketone or this structure, which they don't have. All right, which they don't have. It reacts with hot acidified to give a compound with 3 carbonyl groups. In fact, this will be oxidized, this will be oxidized, this will be oxidized, and all will give you a ketone. And let me see, maybe just one more here. This is actually a ketone also. So I mean, there'll be like at least minimally there'll be 4 already, right? So I guess this one is also wrong. Okay, it reacts with aqueous bromine to incorporate up to 6 atoms of bromine. So if you react with bromine, where would the Br go to? Okay, for phenol, right? So this will be Br, this will be Br, because phenol will react with aqueous bromine. And I think that's it. Yeah, so this is wrong. You can't have 6 atoms of Br. Okay. So it reacts with excess sodium metal to produce 2.5 moles of hydrogen gas. So what's the reason? Let's try. So where would all the hydrogen come from? Okay, the hydrogen will come from these places. There's a H from here. 1, 2, 3, 4, 5. All right. So which means it will actually react with sodium. Okay, this is sodium, right? So 1, 2, 3, 4, 5. So you react with 5 sodium. All right. So you get the salt. Okay, plus since you get 2.5 H2. Okay, right, so I already highlighted all the H, 2, 3, 4, 5, yeah. So 2.5 moles of hydrogen, so answer is D. Okay, let's look at the next question. How many moles of PCl5 will react with the products form from heating 1 mole of hex 3 in 1,5-diol, which is this molecule. So when you heat this in the presence of potassium KMnO4, so I'll just write down MnO4 minus and H plus and heat. All right, so what you end up getting is there's a primary alcohol, there's a secondary alcohol, and you have an alkene. Is okay? So the secondary alcohol will be oxidized to a ketone, and this alkene will be broken over here, oxidative cleavage. You're gonna get COOH, and the other side also COOH. Can you see that? COOH on the side. And this carbon will, since it's a primary alcohol, it becomes a carboxylic acid. Alright, so now if you're going to react PCl5 will only react with any OH on carboxylic acid or alcohol, which means it's 1, 2, and 3. Alright, so the answer should be C. Okay, so your answer should be C over here. So 3 of them. Alright, okay, let's move on. Next question, question 4. What is true of its enantiomer? This is found to halt the growth of methicillin resistant staphylococcus and in short it's just MRSA and anthrax. Okay, so the thing is, what is true of the enantiomer? The enantiomer is you're talking about is the mirror image, right? The mirror image of this. So we must understand that when you talk about medicine, right, it's very specific. Okay, it's very specific to the substrate, right? Very specific to the substrate. So what I'm trying to say is, what's true of the enantiomer? The mirror image would have a different 3D shape actually, so it will be inactive against the MRSA. Right? So it's very specific for all medicine, right? Normally one of the enantiomer will work and the other enantiomer will not work, right? Because it's very specific based on the 3D shape, right? So that's why the answer is B. Okay, let's move on to the next one. Okay, question 5. What will be produced when the following compound is reacted with cold sodium hydroxide? So cold sodium hydroxide means this could only be an acid-base reaction. This can only be an acid-base reaction, not hydrolysis or anything like that. So acid-base reaction, which means only one of this is an acid that can react with sodium hydroxide, is actually the phenol. Okay, so only the phenol will react and the rest will not react. Okay, so which means for this one here, right, if you can see, the answer will be B, right? So this is the answer, B. Okay, let's move on. So this is the only part that reacts. Okay, lactic acid. Okay, lactic acid causes pain when concentration builds up in muscles. Which reagent will react both OH in lactic acid? So let me just draw out lactic acid first. Okay, this is what it looks like. So hydrogen bromide, actually this hydrogen bromide, they should actually state it's a gas, yeah, it's a gaseous. So this will only react with alcohol. Okay, it will convert the OH to Br. Okay, so it convert over, but it only reacts alcohol, so which is wrong, means it doesn't react with carboxylic acid. PCl5 can react both alcohol and carboxylic acid. It will replace the OH on both of them with Cl, so this is definitely correct. Sodium will react anything with OH, which means it's correct. Okay, sodium hydroxide only reacts with carboxylic acid. Okay, it doesn't really react with alcohol, which means this will also be wrong. So the answer, I'll put it as 2 and 3. Okay, so 6 will be 2 and 3. All right, okay, C. Okay, let's move on next one. Okay, question 7. Okay, let's look at question 7. Which of the following are possible products of vitamin A with excess hot aspect KMnO4? So what happens is it's going to break all the double bonds and also oxidize the alcohol. This is the primary alcohol. Okay, so I'm just gonna break here, these two. All right, so let's see how I'm going to draw it. So the first part, this is how I'm going to draw it. All right, this will become a ketone. All right, this part here also be double bond O. All right, and this part here will become the carboxylic acid. Amy? All right, so I'm trying to draw this portion only. I'm trying to draw this portion only. So if you look at it very carefully, this is actually 1. Okay, actually this structure that I've just drawn is actually 1. Okay, let's look at the second one. Okay, second one, if I break this part, I'm going to draw this part here. Okay, I break here. Okay, so I'm going to draw the middle. So how do I draw it? Okay, so double bond O, OH. Can you see that? Then this will be double bond O. Alright, so if you look at it carefully, this is actually this. This is actually this. Yeah? Again? Okay, so 1 and 2 are definitely correct. Okay, but what happens if you draw the third one, which is this one here? Okay, so if I draw this third one, so 1, 2, 3. Alright, so this is my 1, this is my 2. Okay, let's look at 3. 3 will look like this. Okay, that is what's forming. Can you see that? So that's 3. But you have to realize that this one here is called ethane diuric acid. This is very unstable in the presence of con H2 potassium KMnO4. So this one will surely always be further oxidized by KMnO4, right? By KMnO4, easily oxidized to carbon dioxide. Okay, carbon dioxide and water. Right? So that's why this one they did not allow this as an answer. So the answer going to be 1 and 2. Alright, so that's why it's B. Okay, let's move on to the next one. Okay, which of the following statement about the reaction is not correct? Okay, if you look at it carefully, methanol acts as a Lewis acid. So Lewis acid is actually an electron pair acceptor. Okay, electron pair acceptor. Okay, so that's a Lewis acid. Okay, so does it show that it's an electron pair acceptor? In fact, it's not. This one here is more like it's donating the H plus, right? So it's more like a Bronsted acid. Okay, it's not like a Bronsted acid. It's not really accepting a pair of electrons, right? It's not really accepting a pair of electrons. So it's not a Lewis acid. Okay, so A is definitely wrong. It's not correct. Oh, so the answer is A. Can you see that? The answer is definitely A. Right? Let's look at the rest to see whether it makes sense. Step 2 is a nucleophilic addition across the double bond. Yeah, it's nucleophilic addition, definitely. Because this is your nucleophile, it will take this carbon, right? Delta minus, delta plus, and the electrons goes to the O. Can you see that? So it's going to be nucleophilic addition. Okay, this statement is correct. Methanol can be used in step 3 instead of water. So step 3, if methanol is being used, okay, methanol will probably be able also to donate the H, just like what water has done. Okay, water also has donated the H plus. So methanol, I guess, should be able to also donate the H plus. So potassium can be used as a catalyst. If you notice, OH minus is being used up and then it's regenerated, so it's actually also a catalyst. So the one that's not correct is A. Alright. Okay, let's move on to the next question. Okay, let's try question number 9. The first one, this is an alkene. You can see from here, this is an alkene. So with hot concentrated H2SO4, normally you're actually converting an alcohol. Okay, normally it's with alcohol to an alkene. Yeah, so normally I take this one as being not right. Hot asphaltic dichromate only can actually oxidize alcohol. But this is alkene. Yeah, so that cannot oxidize alkene, so which means this is also wrong. Okay, if I use hot acidic KMnO4, you realize that it will actually be converted. If I use KMnO4, right, it will be converted to actually benzoic acid. Okay, it's what you call side chain oxidation of the benzene ring. So entire side chain will become benzoic acid. Alright, so this is actually also wrong. Okay, why is the last answer correct? Okay, let's see why the last answer is correct. So the first step is like that. Okay, I'm just gonna do the whole thing with everybody. Okay, the first step is you're supposed to use concentrated H2SO4 cold, then followed by water warm. Okay, so you end up, if you follow Markovnikov's rule, alright, Markovnikov's rule, this is what you're gonna get. Alright, so this H row, this one is more, this carbon is more H, you put a H here, and this will be OH. Can you see that? And if you look at it carefully here, this is your iodoform structure. That's why they use alkaline, iodine, and warm. So if it undergoes iodoform structure, right, this is your final product. Okay, this is your final product. So this one you still get C double bond O minus, right? O minus. Yeah, but if you add in H plus after that, okay, and then the O minus will get protonated, and then you actually end up getting COH, right? So that's why it's definitely possible. Okay, so the answer is D for this. Okay, let's try question 10. Let's look at question 10. Okay, question 10, maybe I'll just go straight into the answer. All right, so the answer is actually D. All right, so let's see what is D. So after step 1, the alcohol with dichromate H2SO4 distill, the primary alcohol, this is a primary alcohol, it will be oxidized to an aldehyde. Can you see? It becomes an aldehyde because of the word distill. It doesn't get oxidized all the way to carboxylic acid. So after that, the next step, you add HCN, trace KCN. This is a nucleophilic addition reaction. So you get your cyanohydrin. All right, you get your cyanohydrin. And the last step, okay, I think you can tell very quickly. Okay, the last step. All right, so after getting this cyanohydrin, right, after getting the cyanohydrin, the CN here undergo acid hydrolysis. So they didn't really ask for this, but this should be adding HCl aqueous and heat. All right, so which means the CN will be converted to COOH, right? Undergo hydrolysis, become COH, right? Okay, so let's move on to question 11. This is actually Tollens. This is actually Tollens reagent. So it's a positive test for Tollens, imply it must be an aldehyde. Okay, aldehyde. So definitely we know it's an aldehyde. It's positive at P cell 5, which means it must be either a carboxylic acid or alcohol. Yeah, aliphatic alcohol. Yeah, not. I mean, not really. I mean, it must be alcohol. Can not phenol, right? Okay, negative result when treated with this. Right, this is actually failings. So failing solution is a positive test for aliphatic aldehyde. All right, it's positive test for aliphatic aldehyde. So if it's a negative result, means it's not aliphatic. Negative, they say negative result. So it's not aliphatic aldehyde. So which means since it's already aldehyde, right, means implied it must be a aromatic aldehyde. So I'm looking out for aromatic aldehyde. So this is my aromatic aldehyde, okay, and this is my aromatic aldehyde. So the answer has to be A or C. The other two are, this one firstly no aldehyde group at all, so this is out. This one is still aliphatic. This is aliphatic aldehyde. The A and C are aromatic aldehyde. The A and C are aromatic aldehyde. Okay, so the answer must be either A or C. Let's see whether it fits into other parts of it. So, this is phenol. Oh, sorry. You can see that this is actually phenol. Okay, this is actually phenol, which means it's not, because over here when I say this is alcohol, it's not phenol. Not phenol. Okay, I say not phenol. Okay, so the answer must be A. Wait, the answer must be A. Alright, let's move on. Next question. Right, let's look at question number 12. Alright, let's look at question number 12. Okay, which of the compound 1 has the following properties? It changes the color of acidified dichromate from orange to green. Alright, so it means that something undergoes oxidation. It gives a yellow PPT with warm alkaline aqueous iodine. So which means it must have either this structure, right, or this structure. Okay, but I did mention before, based on this question, I can see that this one can, this and this 2CH3, right? It doesn't always have to be CH3. It could be CH2I, it could be CHI2, it could also be CI3, all right? So all these will give you a positive test. So let's see whether it can be oxidized. Okay, this one here is a ketone, and this is a tertiary alcohol, so which means it cannot be oxidized at all. I'll take it up. Okay, so it's not possible because you have to undergo oxidation from here. Okay, if you look at the next one, I'm checking whether this one has a positive iodoform structure, and I was looking over here, but the thing is this is a O, so which means when I say R, it must be either a carbon or a hydrogen, right? Okay, this R group here. Since this is O, which means this one will not give you a positive iodoform test. B is out. All right. Okay, let's look at the next two. Okay, if you look at this one here, if I try to box this up, actually this one doesn't have the iodoform structure, right? Because you need to have a H, right? This is what it should look like. Okay, but this one is out also. Okay, why is this the answer? Because number one, Let me just draw it out nicely. Okay, so number one, this is actually an aldehyde. Okay, this is an aldehyde. So aldehyde can be further oxidized to carboxylic acid, so it fits into this answer. And over here, this one is actually a positive iodoform structure. It's actually from here. Okay, it's actually this part here. Right, so this positive is just that the CH3 is not CH3, it's CH2I. Right, so it's going to be positive. Yeah, so that's why the answer is C. Okay, let's move on. Next question. Okay, 13. Okay, I'm just going to go straight into why this is the answer. Okay, if you look at question 13, right, I think this one we did in my lesson before. Okay, so C is the answer. All right, the reason is this. Okay, this is like it's like an iodoform test, right? But it's just that it's already part of the intermediate that you're starting with. So this one here, you notice this is your possible iodoform structure, right? So generally, when you add sodium hydroxide NaOD, because iodoform usually is iodine and sodium hydroxide, isn't it? Right. So with sodium hydroxide, but now it's OD, so this part will break. Alright. In fact, this is how it works. Maybe I just show you how a bit of the mechanism. OD minus. So delta minus, delta plus. Alright. So this one will attack this carbon. Alright, and electrons will go to this carbon. So you end up getting CH3. C double bond O, OD plus Ci3 minus. Alright, Ci3 minus is actually quite it can still actually accept a H plus from here, which means but no, it's not H plus, it's D plus. So the final product will be CH3, C double bond O, O minus, and this has become CDI3. Alright, CDI3, just like your CHI3, but in this case it's CDI3. So the answer is C because of this part. So which reaction produces a carbon containing deuterium? C, because this is your product. Okay, so let's move on. Let's look at this question. Okay, what can be a byproduct of this reaction? Okay, what can be a byproduct of this reaction? So 2-bromobutane may be prepared by slowly adding concentrated sulfuric acid to sodium bromide to form hydrogen bromide. So hydrogen bromide, this is formed. Then it reacts with the butane 2-ol. This is butane 2-ol, and then to get this compound. All right. So what could be a byproduct? So if you started with butane 2-ol, okay, maybe I just draw it out very quickly. This butane 2-ol. All right, this butane 2-ol. Of course, the rest are all H's. Okay, we'll just put them in. Right. So one of the possible byproduct is, because you use concentrated H2O4, this is actually a dehydrating agent. Dehydrating agent. So what it can do is can actually remove water. Okay, in this case, I think it's possible to remove water from here. So you can actually get one. Alright, so you get this. So after getting this compound, right, after getting this alkene, they say it's a possible, could be a byproduct, okay? So after getting this alkene, because of the HBr that's present, it can react with HBr, alright? It can actually react with HBr, and you also can get this product here, okay? You can add HBr across the double bond, and you can actually get this product. So these 1 and 2 are actually possible byproduct. Alright, even though 2 you can get it, but it's a minor byproduct. Okay, because if you follow Marconi-Cauchy rule, the H will go here and the Br will go here. But the minor product will be you put a H here on this carbon and put the Br on this carbon, right? The first carbon. So that's where you got 2. Okay, so the last one is kind of strange, but I don't think you can get it because if you look at it carefully, there are 2 Br on the same carbon, so which means this will not happen. Okay, this will definitely not happen. I don't see it happening in this reaction here. Okay, all right, so it's just 1 and 2. Answer is B. Okay, this is for question 14. Okay, let's look at the next one. Alcohol halides can be prepared from alcohol. The first step mechanism involves the following. So what's the role of the alcohol in this step? Okay, so the alcohol here is actually have a lone pair on the O, is actually accepting a H plus from HCl. Okay, it's actually accepting a H plus from HCl. So because of that, it's actually donating the lone pair, right? The lone pair, right? Can you see that? So it's actually donating a lone pair. It can be considered a Lewis base. So a Lewis base is an electron pair donor. Okay, electron pair donor. So it can be considered a Lewis base in this question, right? So that's why it's going to be B. All right. Okay, let's look at question 16. Okay, let's look at question 16. Okay, on heating D with concentrated sulfuric acid, two products are formed, E being the minor product. On heating E with hot asphyte potassium manganate, one of the products gives a yellow precipitate. Okay, I'm just going to go straight into the answer. Okay, go straight answer and show you why that is so. The answer is actually D, right? Let's see why is it so. So let me just draw it out nicely. All right, CH3. This one also another CH3, but I'm going to just draw it out. All right, this carbon has an OH. This one is a CH2, CH2, right, and CH3 over here. Okay, you're going to get two possible products, right? Two possible products. So you can actually, if I take away OH and a H from here, right, I'm going to just draw it out first. This is what I get. My double bond is over here. Right, my double bond is over here. Okay, if I took away OH and a H from here, right? So where would my double bond be? Right, where would double bond be? It will look like this: CH3, CH3, double bond, yeah, H and CH3. Okay, according to Say-Sev rule, you realize there's this thing called Say-Sev rule. Say-Sev rule says the more substituted alkane will be formed. This is a di-substitution because you look at the CC double bond, right? This one is a tri-substituted alkene because you have 3 alkyl groups on the CC double bond. Okay, so this would in fact be your major, all right? This is your major, all right, and this is your minor, all right? Okay, so they want E being the minor product, so I'm just going to use E, all right? E is your minor product, which is this one. Okay, now you're going to heat it with hot acidified potassium manganate, all right? Hot potassium KMnO4. So when you heat it at KMnO4, right, what you get on this side will of course become CO2. On the other side, you get a double bond O, CH3, all right, CH2, CH3. Can you see that? And one of the products give a pale yellow PPT with alkaline equals iodine. This is definitely possible because this one is your methyl ketone. All right, so this will give you, right? So that's how we got the answer. It's actually D. Okay, you can try the rest and you can see that it won't give you the answers actually. Okay, let's look at the next one. This one's a bit tricky, I believe. All right, but you probably have to see a bit of a pattern over here. All right, so how does it work? Okay, 1,2-diol treated with dilute acid, the protonated diol undergoes pinnacle rearrangement as shown. Which of the following products is not formed by this rearrangement? Okay, so maybe I think I'm going to show you roughly the mechanism. So how you end up getting this product here. Okay, let's see how it's done. So you started with a diol, right? With a diol. Okay, so what it means is this. Maybe I just show you very quickly how this works. Okay, you started with a diol here. Okay, diol here. So in the presence of acid, okay, in the presence of dilute acid, they say this is what happens, right? I put a H plus over here first. Okay, let me just change it a bit. Okay, so you get the CH3, COH, CH3. Okay, there's a lone pair, this O that takes in the H plus. That's why they drew it this way. You can see there's a H. So the H plus actually, the lone pair goes to H plus, and then the O takes the positive charge. All right. Okay, the next step, what really happens is this. What they're trying to show is this. Okay, maybe just to give you some idea. The OH bond here, there's an OH bond. Sorry, I'm just going to change it a bit. Okay, there's an OH bond over here. Right, the electrons, actually I can take it as the electrons from here goes here, electrons from here goes here. Alright, so what do you end up getting? Okay, what do you end up getting? And over here, I think the electrons from here will go to the O. See, there's a plus over here. Alright, so let me just draw it out. You get CH3, a C double bond O. alright, then this is CH3, this is CH3, and this carbon become a plus, alright, and water is being formed. Okay, see that? And this guy here actually becomes CH3 minus. So since this CH3 minus will attack this carbon, and then you actually end up with the product, which is CH3 double bond O, CH3, CH3, and CH3. Can you see that? Okay. So, but to cut a long story short, I just need you to be able to see what's happening. So you have to your eyes focus on the 2 carbon with the OH. What you need to do is pull out one of the CH3 that's attached to the carbon, or one of the R groups attached to carbon, and put it on the other carbon. Okay. So this CH3 actually goes here. You see that? And on this carbon, alright, you take away water, take away OH, alright, and this side will form a O double bond C. Okay, so let's try. So let's see how we did this one. How you get A. A can be obtained. Okay, A can be obtained when this OH is being kicked out, alright, and the CH3 goes to this carbon. Okay. So it's like you kick out, it's the same concept over here, right? Let's see, this question you have to see a bit of pattern. You kick out the OH from here, and then this CH3 goes to the adjacent carbon, right? So this CH3 goes to this carbon, and you kick out the OH, all right? And then this one becomes double bond O. Okay, so this is how you got the first one. Can you see that? Okay, let's try the next one. Okay, must be able to see a pattern here. Okay, for the second one, you actually kick out this CH3, it goes to this carbon, alright, and then this OH was gone, and then also this one forms the C double bond O. Okay, so that's why you get this structure. Okay, that's why you get this structure. Alright, okay, let's look at the next one, how you end up getting C. Okay, is it possible to get C? Okay, is it possible to get C? Yes, it's actually possible to get C. So very quickly, alright, this is a bit more tricky. I hope you can tell. Okay, this whole group, right, this whole part, this carbon, okay, this carbon was this whole part was kicked out, all right, and it actually went to this carbon. Okay, went to this carbon. Can you see that? So the part that you kick out the CH3, all right, this part will become a double bond O here. Okay, you can see this is going to form a double bond O, and then this OH should be kicked out. Okay, this OH should be kicked out, and this carbon will actually join to this carbon. So if you try to draw it out, it looks like that. It's a bit I'm going to draw the untidy form first, right? So this one, the double bond O, see, and this carbon here will join to this carbon. You see that? So now this becomes CH2, CH3, and this is actually CH3. Okay, so this is what's happening. All right, this is actually what's happening. So if you look at it carefully here, I want you to see a pattern here. In this ring, there's how many carbon? 1, 2, 3, 4, 5, 6. You see? So that's why this structure here, I want you to look at it very carefully. It's actually really this structure over here. Alright, it's actually this structure over here. Okay, so the answer is actually D. This cannot be formed. Alright, this cannot be formed. Okay, you have to, maybe some of you might have to have a bit of, you must spend a bit more time looking at this and see whether you can get the answer. Okay, this is a bit more tricky, this question, right? It's for you to see whether see a pattern and see whether you can derive from the options given. Okay, so that's how we do question 17. Okay, let's move on, next one. Okay, it reacts with compound M. All right, compound M is formed when alcohol N reacts with hot acidified potassium manganate. Okay, and M, they gave you these answers. Okay, I'm going to just go straight to answer. All right, go straight to answer. Okay, for this one, I believe the answer is D, right? So what happens is so this is your N, this N, if you use, you form N when you add KMnO4, right? So KMnO4 is going to oxidize the double bond, and this primary alcohol will be oxidized to a carboxylic acid. This is a primary alcohol. So let's try to draw. So this will become a carboxylic acid. Can you see that? So this carbon will join to this part. Okay, this will become a ketone. And this one will break to become a carboxylic acid. So this answer. So it reacts with 2 moles of PCl5. So I guess I can see why, because you can remove the OH here and the OH from here. So 2 moles of PCl5. PCl5 is alcohol and carboxylic acids. It does not give a yellow PPT when heated with alkaline aqueous iodine. Yes, this compound do not have the iodoform structure. Alright, so this compound doesn't have the iodoform structure. So this is actually your M. Okay, so yeah, that's why it's D. Okay, you can try the rest and see whether it makes sense. Alright. Okay, let's look at question 19. Many but not all organic reactions need to be heated before reaction. So this one, halogenate alkane, for B, for B we definitely need to heat. Alright. This one actually, this is actually normally what we do is ethanolic. The for B is always ethanolic, KCN and heat. Okay. For this one is actually alcohol become alkene is excess, concentrated H2SO4 and heat. Okay, and this one here is always I guess this one is hydrolysis. So you can do, in this case, like it's just like acid or base hydrolysis, right? So you add acid or base and you must heat. Okay, this one here, PCl5 normally is done at room temperature. So it's anhydrous PCl5. It's a very reactive. It will just react. Okay, it will give you a good rate really at room temperature, right? So the answer is A. Okay, let's look at the next one. Ethanol was mixed with excess acidified potassium manganate. The reaction mixture was then boiled under reflux for 1 hour. Right, the organic product was then collected by distillation. Okay, the yield of the product was 75%. Okay, so alcohol mixed with excess acidified potassium manganate and then will boil under reflux. Okay, under reflux means it actually will be converted completely to a carboxylic acid actually. Yeah, and then so the primary alcohol here, all right, will actually be oxidized all the way to carboxylic acid. Okay, oxidized all the way to carboxylic acid, and the organic product was then collected by the yield was 25%. What is the mass of the product collected? So the number moles of alcohol, okay, is equals to 2.76 divided by 46. This gives you 0.06. Right, so the number of moles of acid that should be produced would be 0.06 times 60. That gives you 3.6 grams, right? So since they say 75% yield, so 75% yield imply, all right, 3.6 times 0.75, that gives you a value of 2.7 grams, right? So that's why the answer is C.
Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.